Let's do an example manipulating the equilibrium constant. So say we have a reaction that we want to know the equilibrium constant for, but we don't have it. However, if we have two or more other reactions that we can combine to equal that one, we can calculate the equilibrium constant for the one that we know. So in the reaction above here, we have tin 4 oxide, which is a solid, reacting with carbon monoxide gas, two of them, to make metallic tin and 2 carbon dioxide gas molecules. And then below we have some chemical data for a reaction with tin 4 oxide and hydrogen gas to make water and tin. And we also have a reaction between hydrogen gas and carbon dioxide to make water and carbon monoxide. And using this information here, we can determine the equilibrium constant for the reaction above. So we need to look for how we can combine these two reactions together in order to equal the top reaction, or how we can add them up. You'll notice that tin 4 oxide is on the reactant side in this case and in the reaction that we want, and metallic tin is on the product side. So we're going to leave this reaction alone, and also notice that we have 1 mole here and we have 1 mole there, and so we should be able to just use this reaction as it's written. Now let's check the second reaction. How can we add this reaction to the one right above it to equal our goal reaction? And that is, we'll need carbon monoxide on the reactant side. Well, down here we have it on the product side. So we should exchange the products and reactants. And when we do that, we'll have this reaction. We'll have carbon monoxide plus water going to H2 plus carbon dioxide. And when we turn a reaction around, make the products and the reactants switch places, we take the reciprocal of the K, or the inverse. So this K for this reaction should equal 1 over this K right here, so 0.771, or that value is 1.297. Now we're a little closer to being able to add these reactions together, but there's no hydrogen in this first reaction, and if we were to just directly add these two together, we'd still be left with some, because we're going to need 2 hydrogens to cancel with the 2 up here, and we're going to need 2 waters to cancel up here, and we'll also need 2 carbon monoxides for that. So what I'm getting at here is we'll need to multiply this whole equation by 2 in order to cancel out the things that we need to cancel and get the right numbers of items up in the first equation. So remember, when we multiply a reaction by some constant, in this case 2, we'll have to raise its K to the power of 2, the number that we're multiplying it by. And so since we need to do that, I'm just going to kind of write that right here as times 2 there. And then when we do that, our K will have to actually square. So I'm just going to kind of write that whole thing square like this. And if I take 1.297 and square it, then I will get 1.682. So 1.297 squared equals 1.682. Now, if we add this equation to this one, remember it's been multiplied by 2, then our hydrogens will cancel and our waters will cancel because they're on opposite sides of the equation here. And we'll be left with 2 carbon monoxides and 2 carbon dioxides in the right position. So if we add this equation to that one, we'll get this top equation here. And when we add equations together, we multiply the equilibrium constants. So in order to get the equilibrium constant for this top reaction, we'll take the first K here, 8.12, and multiply it by the K down here, 1.682. So and that equals 13.66. And so that's 13.66 is the K for the above reaction. And that's how we take advantage of our rules in how, if we're changing the equilibrium expression or the reaction, what happens to the equilibrium constant. And you can see how we can take chemical data that we may have and determine chemical data that we want based off of that without having to run additional experiments.